Imagine waking up one morning to a news story that piques your curiosity. A comet from another star system is shining with unusual intensity and, astonishingly, has changed color for no apparent reason. At first, you might assume it's just another sensationalist headline on the internet. However, upon closer investigation, you discover that astronomers are perplexed, mathematical models fail to explain the phenomenon, and there is a string of anomalies so peculiar that even the most cautious scientists cannot ignore them. This is the case of 3I Atlas, an interstellar visitor some have called the most enigmatic object ever observed. I have followed its journey since its discovery, witnessing how its peculiarities, one by one, have forced us to rethink our expectations. Now, after its recent perihelion, the point in its orbit closest to the Sun, it has become brighter and bluer than ever before. In this narrative, I aim to explain step by step how this came to be, why the scientific community is astounded, and what implications this has for our understanding of the universe. To grasp the magnitude of this phenomenon, it is essential to revisit its origins. On July 1, 2025, the Atlas Asteroid Warning System detected a luminous point moving at an extraordinary speed. What initially appeared to be an ordinary asteroid or comet turned out to be a visitor from beyond our solar system. Orbital calculations revealed a hyperbolic trajectory, indicating it was not gravitationally bound to the Sun. It was the third interstellar object detected, following Oumuamua in 2017 and Borisov in 2019. We decided to name it 3I Atlas. Its early detection gave us months to prepare, a luxury we did not have with Oumuamua, which was discovered only as it was already departing. With Borisov, we had slightly more time, but still limited. 3I Atlas, in contrast, offered us the opportunity to observe its behavior throughout much of its journey through the solar system. From the outset, we knew it would reveal something new. We could not have imagined how much. Initial measurements indicated that the object was traveling at over 130,000 kilometers per hour, making it the fastest body observed in the Sun's vicinity. Its diameter was estimated to be between 3 and 5 kilometers, though uncertainty was significant due to the gas and dust coma surrounding it. This size already made it the largest interstellar object detected. However, the most surprising aspect was the alignment of its trajectory with the ecliptic plane. Most interstellar visitors traverse the solar system from above or below, crossing the orbital plane at sharp angles. 3I Atlas, by contrast, seemed to follow the planetary route. Its orbit was inclined only a few degrees relative to the plane in which Earth, Venus, Mars, and other planets orbit. Moreover, its path brought it relatively close to Venus, then Mars, and finally Jupiter, as if it were embarking on a sightseeing tour of the solar system. This statistical coincidence was the first of many anomalies that accumulated over time. The second anomaly became evident in the initial images captured by the Hubble telescope and the Gemini telescope in Chile. These observations revealed something puzzling: a reverse tail, also known as an anti-tail. In typical comets, the tail extends in the direction opposite to the Sun, as the solar wind pushes gas and dust outward. However, in images of 3I Atlas, a stream of material was observed directed toward the Sun. Initially, many assumed this could be a perspective effect. The comet might be ejecting dust particles in a direction that, from our vantage point, appeared oriented toward the Sun. However, spectra confirmed a genuine flow of carbon dioxide and carbon monoxide emanating from the illuminated hemisphere, a behavior that defied the usual pattern. This anti-tail became the second anomaly. As we grappled with the presence of this reverse tail, we began investigating the object's mass. Measurements of its brightness and the effect of radiation pressure suggested that 3I Atlas was far more massive than expected for a comet. Mass estimates soared to tens of thousands of billions of tons. For context, Oumuamua, a modestly sized object, had an estimated mass of a few thousand tons. Borisov, comparable in size to Halley's Comet, reached hundreds of millions of tons. 3I Atlas, however, appeared to be millions of times more massive than Oumuamua and hundreds of times more massive than Borisov. Such a heavy object would need to be either very large or extraordinarily dense. This third anomaly, its colossal mass, suggested that the core was far larger than initially estimated or possessed an exceptionally high density. The fourth anomaly concerned its chemical composition. Comets in our solar system are primarily composed of water ice, mixed with carbon dioxide, carbon monoxide, and other compounds. In 3I Atlas, water was only a minor component. Observations from ground-based and space telescopes, including the Very Large Telescope, revealed that the comet's coma contained large amounts of carbon dioxide and cyanide, while water accounted for less than 10%. Measurements from the James Webb Telescope indicated that the ratio of carbon dioxide to water was approximately 8 times higher than in ordinary comets. Most surprising was the detection of nickel vapor and, in particular, nickel tetracarbonyl, a compound used in industrial metal refining processes. Its natural presence in a comet was unexpected. Additionally, an excess of nickel was observed without a proportional presence of iron, suggesting a chemistry of a different origin. Some speculated that the comet might have formed in an environment unlike that of our comets, perhaps near a hotter star or with a unique chemical makeup. Another anomaly, the fifth, was related to light polarization. When sunlight reflects off a comet's dust particles, its polarization provides clues about the size, structure, and composition of those particles. Observed comets exhibit positive polarization at certain wavelengths. 3I Atlas, however, displayed extreme negative polarization, indicating that the particles in its coma had geometries or internal structures never seen in other comets. This unusual behavior added to the list of unique characteristics. The sixth anomaly was tied to the comet's precise trajectory. Beyond its alignment with the ecliptic, its path led it to pass relatively close to Venus, Mars, and Jupiter at specific times. It was not just the alignment but the timing. Its approaches to these planets coincided with windows that coincidentally obscured it from Earth's view. For instance, during its perihelion and approach to Venus, the comet was hidden behind the Sun. This randomness raised suspicions among some researchers, who considered it too great a coincidence. Others pointed out that the distribution of orbits and the geometry of the solar system can produce unusual alignments without requiring extraordinary explanations. The seventh anomaly emerged in the analysis of volatile content. Observations from the Swift Observatory detected hydroxyl radicals, which form when ultraviolet radiation splits water. The observed amount indicated that the comet contained very little water, reinforcing the idea that its core formed in a region rich in carbon dioxide and poor in water. Curiously, this chemical profile resembles that of comets originating in the inner regions of star systems, where heat prevents water condensation. Yet, if it formed so close to its parent star, how was it ejected into interstellar space? And how did it survive so long? The eighth anomaly arose when the Jet Propulsion Laboratory detected that the comet was experiencing non-gravitational acceleration. NASA calculated a velocity change of hundreds of kilometers per day squared. These figures suggested that, if the acceleration was caused by gas expulsion, the comet would need to lose a significant percentage of its mass in a short time. However, no sufficiently large dust cloud was observed to account for this loss. This discrepancy sparked curiosity and, naturally, the imagination of those considering possibilities beyond the conventional. With these anomalies in mind, the anticipation for perihelion was immense. Professional and amateur astronomers were ready to observe any changes in its behavior. NASA and the European Space Agency organized missions to collect data. In late October, the comet reached its minimum distance from the Sun. During those days, it was invisible from Earth, but solar satellites continued observations. It was then that the ninth and most recent anomaly emerged, an unprecedented increase in brightness and a color shift. Data from the stereo A SOHO and GOES instruments showed that, within a few days, the comet became significantly brighter. The light curve, plotted as a function of distance from the Sun, rose sharply in an unusual manner. Typically, comets grow brighter as they approach the Sun, but this relationship usually follows a law where brightness increases inversely proportional to the square or cube of the distance. In the case of 3I Atlas, the brightness followed a law inversely proportional to the distance raised to the power of -7.5. This meant that each small approach to the Sun resulted in a colossal increase in brightness. No known comet has exhibited such an extreme relationship. This sudden surge left astronomers baffled. Some considered a massive material ejection, others, the sublimation of hypervolatile compounds suddenly exposed. But the most striking feature was the color change. Color photometric measurements by the LOSCO instrument of the SOHO Observatory demonstrated that 3I Atlas was bluer than the Sun. Under normal conditions, comets exhibit reddish or yellowish hues because dust scatters light, attenuating blue tones and emphasizing reds. Moreover, a cold surface should emit relatively redder light. In this case, the comet appeared to glow in the blue spectrum. Avi Loeb, in an interview with a magazine, expressed surprise that the comet was bluer than the Sun. He noted that dust typically reddens sunlight and that a colder body should appear redder. Therefore, He proposed considering the blue color a new anomaly. Scientists analyzing the data agreed that this color-suggested gas emissions significantly contributed to the comet's brightness. In other words, it was not just reflected sunlight but light emitted by excited molecules in the coma. How are these molecules excited? The possibilities are varied. Carbon dioxide and carbon monoxide molecules, when ionized by solar radiation, can emit photons in the blue range. It was also hypothesized that ammonia could produce a bluish hue when scattered and ionized. However, the intensity of the observed blue was difficult to explain with conventional mechanisms. This led to the question that has accompanied us since the phenomenon's detection: why does it shine so brightly? And why is it blue? Analyzing the photometry, it was determined that the comet reached a brightness of nearly 9 magnitudes, making it visible with small amateur telescopes. No one anticipated such a rapid increase. According to scientists who published a preliminary analysis, the reason remains unclear. This puzzle gave rise to new theories. The simplest explanation is that, as it approached the Sun, part of the comet's crust collapsed, exposing fresh material rich in hypervolatile gases. These gases sublimated violently, producing a plume of ionized gas that emitted blue light. However, the volume of gas needed to account for the brightness and color would imply that the comet lost a significant portion of its mass. Another possibility is that the comet had an exotic composition with compounds that are easily excited by ultraviolet radiation, generating a blue glow. Some drew analogies to the blue flashes of certain electrical discharges or the aurora borealis. The interaction of the solar wind with the comet's gases could produce fluorescence. Yet, none of these hypotheses fully explain the speed and scale of the change. Some researchers advocated the idea that it could be a sign of artificiality. They argued that the rapidity of the brightness increase and the blue hue resemble what we might observe if a plasma reactor or hyperdrive were activated. It was also suggested that the color could stem from panels or intelligent materials designed to blend with the solar environment. Avi Loeb, for instance, does not rule out that some of the comet's anomalies could point to technology. In his analysis, the combination of orbital alignment, anti-tail, enormous mass, coincidences in planetary approaches, atypical chemical composition, extreme negative polarization, possible connection to the WOW signal, non-gravitational acceleration, and color shift is too improbable to be mere coincidence. Therefore, he proposed the Loeb scale, in which the object scores 4 out of 10 for the likelihood of being artificial. While this scale is subjective, it reflects the intensity of the debate. However, the majority of scientists prefer to seek natural explanations before considering technological hypotheses. Tom Statler, a NASA scientist, emphasizes that nature can produce behaviors that challenge our expectations. The history of astronomy is replete with examples of seemingly inexplicable phenomena that eventually found natural causes. For instance, Mercury's orbit did not align with Newtonian gravity until Einstein developed general relativity. The rotation of galaxies led to the discovery of dark matter. Most astronomers believe that, eventually, we will find natural explanations for each of 3I Atlas's anomalies. As discussions intensified, data continued to pour in. Solar missions recorded disturbances in the magnetic field around the comet, which could account for some of the blue light. Streams of ionized gas, interacting with the solar wind, generated their own emissions. Ground-based observations, once the comet emerged from solar conjunction, showed it remained bluer than usual, suggesting its composition had changed permanently, not just temporarily. Missions headed to Jupiter, such as JUICE, were preparing to aim their instruments at the comet in November, hoping to measure its surface temperature and detect possible cavities or fractures. The Juno probe, orbiting Jupiter, plans to conduct microwave observations in late March when the comet passes at a relatively close distance. These measurements could reveal the comet's internal structure and mass distribution, shedding light on the cause of the acceleration and color. Meanwhile, the question of whether the comet broke the laws of physics continued to echo in the media. Strictly speaking, the laws of physics are descriptions of the patterns we observe. If something does not behave as expected, it may indicate that our descriptions are incomplete. This is not the first time we have faced such a situation. When planetary orbits did not match Ptolemy's models, heliocentrism emerged. When Mercury's orbit did not align with classical gravity, relativity was born. When cathode rays defied models, quantum mechanics arose. This is how science works. In this case, 3I Atlas has shown us the diversity of interstellar bodies. It has reminded us that not all comets are dirty snowballs. There are comets rich in carbon dioxide, with highly massive cores, unusual jets, and atypical colors. Moreover, it has motivated us to study more closely how comets interact with the solar wind, how their compounds ionize, and how they behave when approaching the Sun. Some suggest that these phenomena may indicate that star system formation processes are more diverse than we thought. If a comet forms near a star that no longer exists, ejected by some instability, and travels for millions of years through interstellar space, its composition may be extraordinary. Some researchers have proposed that objects like 3I Atlas could be planetary seeds, rock and gas cores formed in protoplanetary disks and then ejected. If such cores are captured by other star systems in their early stages, they could accelerate planet formation. This suggests that 3I Atlas is not just a purposeless rock but a cosmic building block with a role in the architecture of star systems. It has also been suggested that its characteristics could result from chemical reactions between silicates and gases that do not occur in interstellar space, implying a complex geological history. In any case, the key is to continue observing and collecting data. The comet will pass closest to Earth in December, at a distance of about 170 million kilometers. While too far to be a naked-eye spectacle, it will be the ideal moment for telescopes to capture its light without solar interference. It will then head toward Jupiter and ultimately vanish into the vastness of space. We have only a few months to seize this unique opportunity. Every observation will be valuable. We may solve the mystery of the blue color, proving it results from natural emissions of excited gases. Or we may detect patterns that reinforce the idea that something extraordinary is occurring. In science, both scenarios are fascinating. What we cannot afford is to ignore the anomaly or resign ourselves to not understanding it. The story of 3I Atlas also teaches us the importance of transparency in scientific communication. NASA faced criticism for its caution and lack of updates during perihelion. It is true that an administrative shutdown complicated the release of some data. However, in the absence of official information, rumors and extravagant theories proliferated. Some believed NASA was concealing a groundbreaking discovery. Others thought a propulsion system had been detected. There were even those who saw the comet as a harbinger of apocalyptic events. This situation reminds us that science must be communicated clearly and consistently to avoid misinformation. As scientists, we have a responsibility to share what we know and what we do not know. Publishing in specialized journals is not enough. We must tell the stories behind the data. Personally, I find myself balancing fascination and caution. I am thrilled by the idea that a comet can challenge our models and compel us to refine our theories. I am awestruck by the fact that we can detect an object from another star system and track it for months. However, I must also be cautious of explanations that invoke extraterrestrial technologies without solid evidence. Technosignatures, signals of non-human technology, are a legitimate field of study but require compelling proof. It is not enough for something to be improbable, it must be demonstrated that no natural explanation exists. At the same time, we cannot close the door to the possibility that advanced technologies, based on principles we do not yet understand, may exist. The balance between openness and skepticism is the heart of science. Many people ask me what I think about the possibility that 3I Atlas is a spacecraft. My response is always the same: truth is not decided by vote but by evidence. Should we one day detect unmistakable signs of engineering in an interstellar object, it would be a monumental leap. But until then, every anomaly must pass through the filter of rigorous analysis. In the meantime, I relish the curiosity this comet has sparked. Science has rarely been so popular in mainstream culture, and that, in itself, is a gift. As the comet moves away and its brightness fades, its legacy will endure. 3I Atlas has already left its mark on astronomy. It has inspired new research into orbital dynamics, the sublimation of hypervolatile gases, the interaction of comets with the solar wind, and the diversity of interstellar bodies. Perhaps the next detected object will share some of these characteristics, or perhaps it will be entirely different. The lesson is that we cannot generalize from 2 or 3 examples. There are millions of interstellar comets in our galaxy, each with its own story. Observing them is like opening letters in a cosmic correspondence. Each one reveals something about the star that ejected it, the processes that shaped it, and the nature of the space between stars. I do not wish to conclude without reflecting on how we interpret anomalies. When something seems to defy the laws of physics, the initial reaction may be dismissal or disbelief. Yet anomalies are the spark that ignites revolutions. The anomaly in Mercury's orbit led Einstein to a new theory of gravity. The inexplicable blackbody radiation gave rise to quantum mechanics. The accelerated expansion of the universe led to the concept of dark energy. Perhaps 3I Atlas will not lead us to a new fundamental theory, but it will undoubtedly force us to refine our models of comets, rethink our understanding of interstellar objects, and ask questions we had not previously considered. This, in essence, is what drives science, transforming perplexity into knowledge. If you have read this far, I hope you share my enthusiasm for witnessing a captivating chapter in the history of astronomy. 3I Atlas has captured attention with its unprecedented brightness and unexpected blue color. But the true story goes beyond that. It is the story of a comet that compels us to view the universe with fresh eyes. It fills me with humility in the face of the cosmos's vastness and how little we know. It motivates me to keep learning and sharing what I discover. If this story has inspired you, I invite you to share it, show your support, and subscribe to our channel. I ask this not out of vanity but because the more of us who love science, the stronger our voice will be in defending the importance of research, curiosity, and truth. 3I Atlas will continue its journey, slowly fading away, but it will leave a legacy that endures in our memory. And we will remain here, ready for the next visitor that challenges our laws and in doing so, teaches us something new.